So, as you remember, yesterday you collected all this data using this spring and pulling it and pushing it, measuring the spring displacement as you applied different amounts of forces. Today we're going to analyze that. So, you should have already made a graph and you should have already written an equation for the line. But now we're going to take it one step further. Ooh, yeah. So, to help us in this, I made a graph, which I'll show you in a second. But I wanted to show you that I didn't use any negative forces. All I did was just use positive forces to make this graph. So when I did that, I got a graph that looked like this. And so there's this nice, beautiful graph. Notice, again, all of the values are positive when I run a linear fit. And because it's a simulation, you should be getting a correlation or an R value of 1 with a y-intercept of 0. So no big deal. And so I just wanted to take a minute and I wanted to write the equation for you here. And so if I remember that the y-axis is force, I've got this thing right here, which I'm going to do. So I'm going to write the equation here. I'll increase the size a little bit so we can see it. Force is equal to, and the slope was 200. And because it's rise over run, it is newtons per meter, times your x variable, which is the spring displacement, which technically should be delta x. I just don't have an easy way to do that here. And that's it. No y-intercept. So this is the equation right here. That's it. Now, there's something else about this graph that is really, really interesting. Notice that on the simulation here, the slope of the line was in newtons per meter. And what do you know? That spring constant is 200 newtons per meter. Wait a minute. I bet all of you guys, and this is true, the equation for this can be simplified. Your slope right here is going to be whatever the spring constant is that you held constant. So I'm going to simplify that to this equation. F is equal to K times X. Knowing that F is the force exerted on the spring, K is the spring constant, and delta X is the spring displacement. Now note this about the spring displacement, or the spring constant. When I look at this spring here, if I increase the spring constant, it gets thicker. And if I apply more force to it, notice how the displacement doesn't get very big. So the spring constant is defined as this. It is the amount of force required to displace a spring by 1 meter. So therefore, if the spring constant is 1,000 newtons per meter, it's going to take 1,000 newtons of force to displace that spring by 1 meter. Whereas if it's 100 newtons, it's only going to take 100 newtons to displace at 1 meter. So basically, the thicker the spring, the higher the spring constant. And that's going to be harder to get it to actually displace from the spring value. So that is the line.